Dear colleagues, I'd like to tell you about optoacoustic angiography for assessment of experimental tumor vascular reaction to radiation therapy. Radiotherapy is a well-known method of cancer treatment, and for quite a long time, there has been debate about what is the main factor of influence, a direct or indirect effect on tumors through the vessels. It has been shown that tumor vessels are one of the targets of radiation therapy, and a degree of treatment impact to the neoplasm depends on the vascular response and macroenvironmental changes. Various dose-dependent vascular effects are known. In the case of irradiation up to 10 gray, there is a temporary increase in oxygenation and perfusion associated with the activation of inosine. In the case of high dose irradiation, more complex effects arise. Decrease in vascular volume, permeability, redistribution of blood flow through a smaller number of more blood-filled vessels. Regression of endothelial cells is observed, and as a consequence, destruction of newly formed vessels and a decrease in vascularization. Optoacoustic angiography allows convenient visualization of blood vessels, which makes it possible to evaluate the effectiveness of different treatment protocols. Monitoring tumor response to radiation therapy using optoacoustic angiography is an important stage for the development of new methods of non-invasive bioimaging, identification the role of vascular system in tumor response to treatment, and development of new approaches to radiation therapy. Vascular mapping by the optoacoustic method occurs due to the registration of ultrasonic radiation induced by a laser in different forms of hemoglobin. Nanosecond pulses are absorbed by biological chromophores, mainly hemoglobin, and a local thermal expansion launched. Optoacoustic method allows to use both benefits such as optical contrast, but ultrasound resolution and depth of investigation. Ultrasonic waves in the megahertz range visualizes tumor vessels location with micrometer spatial resolution. Our optoacoustic setup scheme is shown on the screen. Probing pulses generated using a laser operating at a wavelength of 532 nanometers. The system response allowed to visualize 40 nanometers blood vessels at up to 2.1 millimeter depth. Ultrawide bandwidth 100 kilohertz till 100 megahertz made of PVDF film was used, allowing to image both the micrometer-sized blood vessels well as much millimeter-sized blood-containing structures. Laser shots coordinated in time with the stage of movements pass through the fiber optics bundle and penetrate tissues. The optoacoustic data processes using bandpass filtration, delay reconstruction, and vascular quantification. Tumor areas, vascular density, vessel segment size are interpreted in MJ. The experiments were carried out on 14 6-week-old female biopsy mice bearing marine colon carcinoma. Irradiation was performed at the 7th day of tumor growth. Two groups of animals received a single dose irradiation of 6 gray and 12 gray locally. Optoacoustic investigation was performed before irradiation, as well as on the 1st, 3rd, 6th, 8th, and 10th day after it. Tumor volume was measured at the same days. Tumor volume was calculated by the formula shown on the screen. In untreated group, significant increase of tumor volume was detected starting from the 8th day. Both 6 gray and 12 gray irradiation groups inhibited tumor growth at differences between untreated and treated groups were observed on 15th day. This proves the significant radiotherapy impact on the tumor development. Optoacoustic signal was divided into 3 frequency bands provided by corresponding filters: high pass, band pass, and low pass that were used for future extensive analysis. Higher frequencies allowed to highlight the smallest vessels, while the lower frequencies allowed to visualize possible large hemorrhages. Images of tumors shown on the slide formed by superimposing data from the three frequency bands. According to optoacoustic data, by the beginning of the monitoring period, ST26 had a significantly developed circularity system. On the 6th-day growth, branches of tumor vessels and normal tissue are clearly visible in all ranges of ultrasound frequencies after optoacoustic data reconstruction. The characteristic features of the tumor vascular bed is entanglement and tortuosity in comparison with healthy tissues are expressed. To analyze the state of the tumor bloodstream, the following parameters were selected. Vascular density and segment size. The last parameter may indicate the vessel size as well as demonstrate vascular shape. Destruction of small vessels in high range. After radiotherapy treatment is evident, segment size and vascular density value drop. 6th grade treated groups showed differences in vascular density and segment size values with untreated groups on the 10th day. Vascular density values of 12th grade treated group decreased after radiation, while segment size values demonstrated the decreasement until 15th day of experiment. This fact may indicate the effects of radiotherapy on the tumor vasculature, specifically the injury of the irradiated vessels. Vessel amount restores on the 10th day, but the size and shape changes saved until 15th day of the experiment. Next situation was demonstrated in the middle range. Vascular density decrease was started from in 24 hours after radiation and served until 13th day. Both group segment size values decreased relative to untreated on 8th day and recovered by the end of the monitoring. It is interesting to note a different vascular reaction in the mid-range from the small vessels. A decrease in vascular density was revealed during a long period of monitoring, but short-term in segment size. Low range showed different results. Group segment size differences between 12th grade and untreated, 12th grade and baseline on the 8th day may indicate formation of hemorrhages as a result of vessel destruction. Immediately after radiation, hemorrhages are formed and up to 10th day an increase in values is observed relative to the control. Specified changes observed until 15th day of experiment. The 6th grade group differed from the untreated group only on day 15th, while the differences in the 12th grade group were set at 8th day. All this may prove dose-dependent reaction after irradiation. Vascular density and segment size of treated tumors in the high and middle range shown a decrease. At the same time, slight growth of the same parameters were observed for vessels of low range. To sum up, 12th grade irradiation gives more pronounced impact on 6th grade than 6th grade. Dose dependence was demonstrated despite reversible vascular changes. Differences in the average value of segment size and vascular density during observation made us assume that the negative effect of radiation therapy consists in violation of the integrity of blood vessels. It's worth noting the different responses of small and medium vessels after radiotherapy. Small vessels show long-lasting segment size changes, but mid-range vessels vascular density changes. I'd like to thank our colleagues from Lobachevsky State University, Institute of Applied Physics for Health, and the Russian Science Foundation for financial support. Thank you for attention. I will be glad to answer your questions.